Okay, so Unit 5 was all about probability. I don't know if you guys, I doubt anyone's looking ahead to remember and kind of recall what these different units are about. That's okay, that's what class is for. But this is one that when we go through it, you might remember, oh my gosh, there are a bunch of really kind of head scratcher problems in this unit. So we'll go through some of those today. And this deals with mutually exclusive and independent events. And the key thing there is that if they are mutually exclusive, we can just use the addition rule. And that says that the probability, the probability of A or B is equal to the probability of A plus the probability of B. Pretty straightforward. If you have independent events, you can just use the multiplication rule that says the probability of A and B is equal to the probability of A times the probability of B. All right. And this is where we need to kind of remember the and, the or, and the complements. So I've already used, oops, I said and accidentally wrote or. This is probably A and B. So yeah, we have and, which looks like that, or, which is the U. You can think of a union. And then complement would be like the probability of A complement. And that's going to be just 1 minus whatever the probability is. And then we ended up coming up with some really crazy stuff where we would say maybe the probability of A complement and B complement and C complement. And we don't even want that probability. We want the complement of it all. So with that, we can come up with some really crazy scenarios, and the numbers are all there. So this is the hard part of it, coming up with what our probability calculation needs to be. But then from there, it's just multiplying numbers, subtracting. It's more of a wrapping your head around the problem than the calculation itself being challenging in any way. All right. So maybe I shouldn't have cleared everything, but that's okay. The other stuff that we had in this, and there's more to it. I'm not covering everything, like simulation was also as part of this, but general addition rule. This is if it's not mutually exclusive. So the probability of A or B when not mutually exclusive would be probability of A plus the probability of B minus the probability of A and, keep doing that, A and B. No, I had it right. Why are you guys letting me make mistakes like that? Okay, now the last one is the general multiplication rule, which says the probability of A and B is equal to the probability of A times the probability of B given A. All right, and then one of the ideas that I didn't put up here as much, we talked about independent, but this is the special case when these are not independent, because when they are independent, we know that the probability of B on its own is equal to the probability of B given A. So these two are equivalent when they're independent. So we can just substitute and we have the simpler calculation to do. All right, and if any of this isn't making sense, it's not coming back to you, then this might be something you want to put a star next to and say, I need to go back and review these probability rules. All right, let's jump into some problems with this. Mateo plays in the school basketball team. From past history, he knows that his probability of making a basket on a free throw is 0.8. Suppose he wants to create a simulation using random numbers to estimate the probability of making at least 3 baskets on his next 5 free throw attempts. Which of the following assignments of the digits 0 to 9 can be used for the simulation? So we know that 8 of them should represent success, and then 2 of them should represent failure. So I want to find a situation where that's taking place. I'm not going to read through all of these, but if I look at this one, I can see that 0 through 7 representing making a basket, well, that's 8 outcomes represents making, and 2 outcomes represents not making a basket. So this fits, that would be my choice. If we read all the rest of these, we would find that none of the others work appropriately. Okay. So this, we are looking at a large customer service department at a store, or a large store that has a customer service department, and 1/4 of all customers who go to the service department ask help finding an item. Uh, and based on the one important assumption is that these are all independent. This is going to allow us, the fact that they're independent allows us to use the multiplication rule, not the general multiplication rule. So that's an important distinction. So what is the probability that at least one of the next 4 customers will ask for help finding an item? It's this at least right here that, if you remember, if it asks for what is the probability that one will, that's actually not as bad of a calculation. If it says what's the probability that all of them or none of them, so all of, none of, or some specific amount isn't necessarily bad, but this at least one gives us 3 outcomes. So we could have 0, 1, 2, 3, or 4 customers come up for help finding an item, and all of these are success conditions. The only failure is 0. So this is where it's actually best to find the probability of no successes and get the complement of that. So that would mean that the first customer, so if we think about it as the probability of any random person asking for an item, that's, I'll just get probability of I, meaning item, is 1 in 4. Well, the probability of not asking for an item is the complement of that, and that's 3 in 4. So I want, out of 4 customers, all 4 of them to not be looking for an item. So not looking for an item, and not looking for an item, and not looking for an item, and not looking for an item. And then once I get that, this is my failure condition, and I want the complement of it. So if you can wrap your head around what we just ran through, then we can just plug in some numbers. And this is essentially going to be 1 minus the probability of not looking for an item is 3 in 4. And there's, because it's and, I'm multiplying, these are independent. So I'm basically multiplying 3/4 to the 4th power. And there's my answer. Now, you don't have to think through this problem exactly the same way, but you should come up with this answer. So maybe you do it in many more steps, and that's all well and good. Okay, but there we go. We can come back to this later if you have questions on it. The next one, we've got an electronic device that has 3 components. The probability of failures are given right here for each A, B, and C. If one component fails, the entire device fails. So what's the probability, if they're all independent of each other, what's the probability that the device will not fail in 1 year? So I'm just going to say the probability that A fails, I'll just put probability of A is 0.01. The probability that B fails is 0.03. The probability that C fails is 0.04. So the complement of those we can figure out real quick. Sorry about that. And the probability that C won't fail is 0.96. So we want all of these to not fail. So we want A to not fail, and B to not fail, and C to not fail. That's the only success condition that we can have here. So you can almost think of this, what's the probability that, if we think about it like in terms of the last problem, like what's the probability that at least one fails and the complement of that? But anyways, probability that none of them fail, which would be basically just 0.99 times 0.97 times 0.96, which gives us 0.922 for our answer. Now, with the answer choices as given, that might be your expectation anyway, because that's really the only one that looks as promising. So there we go. This is a kind of problem that caused a lot of headaches before. And remember, mutually exclusive events are ones where, I didn't say this at the beginning, but the probability of A and B is 0. So that might ring a bell. You could also talk about it in terms of the probability of A or B has to equal the probability of A plus the probability of B. That has to add up, and there can't be any overlap. Okay, so let's actually set up a Venn diagram first of all. So there are 78 students overall for this high school science teacher. So there's 78 in this, in the total amount. Of those, 35 are in band. I'm going to use B. They tell me to use B as this event. 35 are in band. Sports, we've got 32. And the people who are not in sports is 16. So what I want to do, I think I want to use this formula right here to make it make a little bit more sense. I know that to be in band or sports, it's going to be the total 78 minus the people who aren't involved in either. So there's going to be 62 people involved in band or sports. So I'm going to take that total. I'm going to plug it in right here. That's going to be this value. So the probability of A, which in this case I'll say that's for band, probability for band is, well, it's technically, now maybe it's not fair to say the probability. We could put all this over 62, and that's technically the probability. So that is maybe a better way of thinking about it. But I just want to talk about it in terms of raw numbers. So these numbers have to add up to 62 for these to be mutually exclusive. The number of people in sports is 32. If these add up and it's exactly 62, then these are mutually exclusive. But if it doesn't, and there's any extra amount, then we're going to have some overlap. So anyways, if I add this up, I get 67. I'm going to bring it down here. So now I have 67 equals 62. That's not true. So it looks like I have an overlap of 5. That means there's 5 students who are involved in both band and sports. All right. So that means this is not mutually exclusive. These two are not mutually exclusive because 5 of my 78 total students are involved in both, which says right here. The probability of band and sports is 5 out of 78. Okay. And I need to make a correction. That should have been out of 78 right here. But there we go. Let's move ahead. And if you need any clarification on that, we can talk about it more later. This other one also caused a little bit of problems. So if we think about this, we've got 17% of students enrolled in a psychology course. Probability of psychology is 0.17. The probability of foreign language is 0.28. The probability of either of them, so of psychology or foreign language is 0.32. Okay, what's the probability that a student chosen at random from the school will be enrolled in both a foreign language and psychology course? There's different ways you can approach this. Here's, I think, what works for me. I'm going to use this. The probability of psychology or foreign language has to equal the probability of psychology plus the probability of foreign language minus the probability of psychology and foreign language. And this is using the general addition rule, because I know these are not mutually exclusive events. So I already know these numbers. 0.32 equals 0.17 plus 0.28 minus the probability of P and F. All right, so if I go through and do my math, I'm not going to do every step. I basically get 0.13 equals the probability of psychology and foreign language. And there it is. Okay. Next one. This is one that on the surface, well, I mean, it might look difficult on the surface, but there's also a very easy mistake to make with this, and we'll go through that. We know that for independent events, the probability of D and E is going to equal the probability of D times the probability of E. And it tells me it's independent. So I know that 0.18 equals 0.6 times the probability of E. So when I do this to solve for E, I'm going to get the probability of E is 0.3. Now, of course, that's not my answer. But here's where you could go wrong. You could say, now I know probability D, I know probability E, so I'm just going to do the probability of D or E, because we already found out that neither of these are correct. The probability of D or E, you might do something like this. I just want to do the probability of D plus the probability of E. Oh, that's easy enough. It's 0.6 plus 0.3. There's the answer. Except, no, it's not that. That is only true if these are mutually exclusive. But one thing that we learned is that you cannot have events that are independent and mutually exclusive. You can't, it's a contradiction. So anyways, what I have to do is I have to subtract the probability of D and E. So now I can solve for this. I don't know the probability of the OR, but I know the probability of D is 0.6. And that's 0.3. I just solved for that. And then D and E is given in the problem is 0.18. So when I do this, I'll get 0.72 for the probability of D or E. And that is the answer right there. Okay. Got a couple more problems here. This is one where you're a contestant on a show, or someone is a contestant on the show, and they have two different events to figure out what their winnings are. They first of all pick a card, and there are three outcomes. You can get $1,000, $2,000, or $5,000. The next is picking a ball from a cup or a chip from a cup or something, and you get either red or white, and that will result in doubling your amount or just keeping the base amount. So this is an excellent situation where you would want to use a tree diagram, because I've got three different outcomes. Okay, so three different outcomes in the first event. So I could get 1,000, I could get 2,000, or I could get 5,000. And the probability, since there's four cards and two of them are for 1,000, so it's 2 out of 4, which means 0.5. So there's a 0.5 probability that I get 1,000. And then these other two are split evenly, so it's 0.25. There's one card for each. So those are the probabilities of that happening. And then for 1,000, for all of them, I could get the red chip. There are 3 red chips. So 3 out of 5 gives me a 0.6 probability. 2 out of 5 gives me a 0.4 probability. And this red chip, they actually give it's a nice show. They actually say that the 0.6 probability will double your amount, and the 0.4 probability just keeps it the same. So bottom line, I have a 0.6 probability of ending up with 2,000 right here when I double it. There's a 0.4 probability that it stays the same. With this one right here in the middle, I could have a 0.6 probability of doubling this to 4,000, or a 0.4 probability of keeping it the same at 2,000. And then the 5,000, it doesn't really matter for our purposes because we're only concerned with getting 2,000 exactly, but I could get 10,000 right here, or I could get 5,000. So there you go. Now, these results we don't care about. In fact, the only results we care about are the 2000. So what I can do is I can multiply the probability along these tree limbs. So 0.5 times 0.6, there's a 0.3 probability that this is the outcome. And I can do 0.25 times 0.4, which gives me 0.1. So these probability added up, these are mutually exclusive events. You cannot have both of these happen. So I can just do a straight addition and get 0.4 as my answer. Now, if I did find the rest of these probabilities right here, it doesn't matter for this problem, but if I did, this would all add up to 0.1. Oops, 1.0. So 100% basically. And there we go. And of course, now you're thinking, or you've been thinking, yeah, this is totally different from a lot of the other stuff we do in the class. Probability is kind of its own thing. In fact, there's a separation between statistics and probability. This is the probability stuff. It's kind of its own thing. But hopefully you're remembering enough of this and it's not that bad. So this one right here is actually very much like the first one we did, or the second one we did. A police officer is using a radar device to check motor speeds. Officer estimates that 40% are going to be speeding. So the probability of speeding is going to be 0.4. Assuming that the police officer's estimate is correct, what is the probability that among 4 randomly selected motors, the officer will find at least one driving more than 5, so at least one speeding? And again, at least one means that out of 4 possible people who drive by, the only failure condition is 0. All of these count as successes for this scenario. So we're going to find the probability that no one is speeding and then take the complement of that. So the probability that this person isn't speeding, and this person isn't speeding, and this person isn't speeding, and this person isn't speeding. And then once we have that, I want the complement of all of that. So probability of speeding complement is 0.6. And what I can boil this down to is 1 minus the probability, which is 0.6 raised to the 4th power, because there's 4 people. So 1 minus 0.6 to the 4th power gives me 0.8704. In fact, this is pretty much exactly the problem we had to begin with, or that second problem we looked at, but now we're actually calculating it out. And there's your answer. All right, we are not looking at an FRQ today. We've got those problems we ran through. Again, if you want to come back to any of these, we can look at any of them, but you do have a Unit 5 FRQ. Make sure you're taking pictures and submitting them. Trying to think if there's anything else. So one thing I didn't specify yesterday is that there are some problems that kind of start maybe at the bottom of the page that obviously I don't want you to do those because I just didn't cut it off completely. So just do the FRQ that's completely on the pages that I have there. And if there's any partial problems, ignore them. I don't know if there's anything else I needed to mention, but make sure you're working on your projects and everything else that you need to do in order to raise your grade here at the end of the year. If you have any questions, stick around. Otherwise, you can have a wonderful day and I will see you tomorrow.
Thanks, Mr. Davis.
Thank you, Mr. Davis. Have a